data engineer, but as Kate said, I didn't start out as a data engineer. I started my career as a software engineer. I was a software engineer for about 8 or 9 years. And then I moved into the data space. And for the longest time, I kept thinking of myself as a software engineer surrounded by data people. But just recently, I've started working with software engineers again, and I now realize, no, I am a data engineer. So, hands up if you write code for a living. Keep your hand up if you have had a moment when you were writing code when it was a little bit boring or a little bit repetitive. Yep, me too. So I had one of these experiences and I thought, hey, wouldn't it be great if I could get a machine learning algorithm to write this code for me? And my talk today is going to step through the process I went through to try and make this happen. So before I even started, I had some rules that I wanted to follow. And they were these. The first, experiment. Write a hypothesis, write some tests, prove or disprove it. Capture data about the process in a systematic way right from the start. And just, it's okay not to have all the answers up front. The second was to apply software engineering best practices where possible. So this was taking all the good stuff I had learned when I was a software engineer. Things like source control, writing unit tests, refactoring, and applying them to the process where they were applicable and useful. The next was use just enough infrastructure. So machine learning is a process, and you get some data, you clean it, you train it on some infrastructure, and it's really easy to get sucked into a tangent and spend days and weeks, trying to define the perfect infrastructure to run your code on. But that's not what's important. What's important is delivering value in your machine learning model. So I set a rule to try and catch myself when I was going on these tangents, and use just enough infrastructure to solve the problem at hand. The second rule, or the next kind of amendment to that rule, was to use just enough infrastructure and data. So machine learning algorithms are data hungry. And a lot of the time, just throwing data at them can make your model better. But using more data requires more infrastructure. And suddenly you're spending a lot of time doing stuff that really isn't core value. Like, what's the smallest test that you can write to prove something? Before I get too much into the details of what I did, I'm going to do some background. And the reason is that for machine learning, I'm going to talk about training a model. I'm going to talk about transfer learning. And I just want to make sure that everybody in the room has an understanding of just a high-level understanding of what I mean when I say those things. So for this, we're going to look at a basic machine learning model. It's called a fully connected model or a multi-layer perceptron. Our use case is we want to build a model that can classify images. So say we have a data set, and we want to be able to classify these images into cats or dogs. This is a supervised learning problem. So we have our data set, we have cats and dogs as images, and each image is labeled as whether it is a cat or whether it is a dog. So we start with an input layer, and this is where we're going to push the data into the model. Next, we add some hidden layers. So each of these groups of nodes is essentially a layer in the architecture. And then we have our output layer. And this layer is going to hold the probabilities of what we are trying to classify. So in this scenario, the top node will hold the probability that an image is a cat, and this one will hold the probability that an image is a dog. Okay, so let's start pushing data through the network. So for this use case, we're going to imagine that the images are grayscale. So each pixel is represented by a value between 0 and 255. So we push the data in the input layer, and then for the first layer, each of the nodes are connected to all of the nodes in the input layer. And each of those connections has a weight along it. So the value in the first node will be a combination of, say, 20 times the weight along the connection plus 100 times the weight along that connection plus 255 times the weight along that connection. And it's just a sum. It's just addition. And similarly for all the other nodes. We also apply what we call an activation function to this summing process. So this is an important part of a neural network, and it allows us to solve more complex problems. Basically allows us to find non-linear data patterns in our data sets. And then similarly, the layers in the next hidden layer, they're composed of the nodes in the first hidden layer. So 20 times the weight along that connection, 0.1 times the weight along the connection, 0.79 times the weight along that connection, plus 0.03 times the weight along that connection. So I just want to pause and give a little bit of intuition behind why we have these hidden layers in this architecture. So the first layer is essentially pixels. And then if you imagine that the first layer learns to compose these pixels into something a tiny bit more complicated, like maybe lines and edges. And then the next hidden layer of the network that learns to take the lines and edges in the first hidden layer and compose them into something just a tiny bit more complicated, like maybe shapes, basic shapes like squares or circles. In the interest of transparency for this basic model, if you were to visualize these layers, it's very rare that you would actually see something that represented edges or basic shapes. In some of the more complicated models you would. But I still think it's a useful way to think about what the purpose of these hidden layers are. So then we connect it up. And the last hidden layer, the layer between the last hidden layer and the output layer, we apply a special function along that to turn it into a probability. And that will tell us what the probability of whether something is a cat or whether something is a dog. So now that we've stepped through all the nodes and how they're connected, let's just talk a little bit about what it means to train a network. So I mentioned previously that this is a supervised learning problem. So that means we have a training set of labeled images. So basically, training is a process by which we compare what the model is predicting those images will be with the actual values. And we do this using a cost function. And essentially, we move backwards and forwards through the network, adjusting these weights and reperforming these calculations as we try and minimize the gap between the predicted labels the model is giving us and then the actual labels. So why is this useful? So we can then take the architecture, like the structure of the model, and we can take those weights, and that allows us to reuse the network. So that allows us to do things like make predictions. So we can take this model and we can recreate it. We can recreate the model that was able to predict cats or dogs using the architecture and the weights. And maybe we can sit behind an API and use it as part of an API. It also allows us to do something really cool called transfer learning. So the reason that transfer learning is important is that it can take a long time to learn something from scratch. So how exactly does transfer learning work? Well, we take our architecture and our network that we trained how to predict an image of a cat or a dog. But say we don't care about cats and dogs anymore. They're gone. Okay, we want to solve for something different. Maybe we've moved to a farm and we want to start predicting images for horse, cow, or a sheep. So I want you to remember back to the intuition behind the hidden layers. So even though this is a different problem, the first hidden layer knows how to represent or how to convert the pixels into lines. The next hidden layer knows how to take those lines and turn them into basic shapes. So this can still be used even though the overall problem has changed. The fundamental components of this network can be used to solve a different problem. So what we can do is reconnect the network, and then we just have to train the blue part. We don't have to train from scratch. And it can take days, weeks, a long time and a lot of infrastructure to train a model up completely from scratch. So this is useful. So transfer learning has been around for a long time for vision. ImageNet is a competition that's been run from, I think, 2010 to 2017. And basically the names there, Inception, ResNet, or AlexNet, they're all names of algorithms that have won ImageNet. So I think before the competition started, the error rate, that's the difference between the predicted labels and the actual labels, for this competition was about 25%. In 2012, AlexNet, that's an algorithm, it got it down to 16%. And then in 2015, ResNet, that got a score of 3.57%, I think, which is better than a human. So there's been a lot of really great work and vision around transfer learning. It's not been the case for natural language processing. Let's give it a drink. So natural language processing is things like trying to understand text or trying to generate text. Well, we don't have the same competition that we had for vision, but just recently, say 2018, there's been a lot of breakthroughs for algorithms. So we've got ULM Fit, we've got BERT, and we've got Elmo. Great Sesame Street names. So we're almost at a point where natural language, that if you were talking to someone on the internet over chat, there's a opportunity, or there's a possibility that a piece of AI could be talking back to you, and you might not realize that it was a human, or it wasn't a human that was talking to you. I'm just going to talk about ULM Fit and Fast AI as well in just a little bit more detail, because I'm going to use this later in my talk. If you're a software engineer and you're interested in learning more about machine learning, I really recommend Fast AI. They've got lots of courses, they've got libraries, and Jeremy Howard, who's one of the founders of Fast AI, along with Sebastian Ruder of NUI Galway, have developed this algorithm called ULM Fit. And basically what that enables us to do is use transfer learning for natural language text generation and text understanding. Okay, I'm going to have a drink. That is the theory part over for a little bit. So I'm going to talk a little bit about the process that I went through. The very first question I had, is this feasible? Is this something that can be done? So I read a lot of papers, and I kind of had this loose idea that maybe there's something in this breakthrough with natural language processing and transfer learning that I could take advantage of in trying to generate code, essentially. Because writing a model from scratch, or building a model from scratch and training it, can take a long time. So the first question I asked is it feasible? And I kind of debated whether I should be using Java code or Python code. And having a look on GitHub, there is a lot of Python code that is machine learning code. And it kind of felt like a little bit inception level wrong to write a machine learning algorithm that could predict code but train it on machine learning code. So that was kind of one of the reasons I chose not to use Python. Another is that Java it can compile, and it seemed like maybe that might be a useful step in being able to generate code, or useful code. So I came up with a series of tests, and I thought that each one is a little bit harder than the other, and then progressively they might be able to get me to generate code, and generate code that is useful. So the first one is, can I generate Java code? The next is, can I generate Java code that will compile? And then, can I generate Java code that will compile and pass a unit test? So I was going to call this section architecture, but it felt like really too strong a word for what it was. It's really more like back of a napkin drawing, back of a napkin sketch. And this is kind of like the overall, before I started, of the high-level view of how I saw it fitting together. So the first thing was to download some code from GitHub, some Java files. The next was to take ULM Fit and train a model on top of that, taking use and benefit of transfer learning. And the output of that would be a model that knew how to predict or how to generate Java code. And then I would take that model and I would do something with reinforcement learning. But that part was really hazy, and I hadn't quite worked out all the details. So let's talk about some of the experiments that I ran. The first one, can I generate Java code? Hands up if you think, before we start, if you think that yes, I could generate Java code. Hands up, show hands. Okay, about half. Okay, so first thing is this is like an infrastructure card of just the kind of the infrastructure that it used. When I saw that part, about downloading code from Git, I thought, right, I can write a script. It's going to download like hundreds of thousands of files. This is going to be awesome. And then I had to stop myself and go, hey, no, is that actually adding value right now? Like, what is the smallest thing that you can do? So the smallest experiment that I could do was using my laptop and manually downloading a single Java project from Git. So this is what the kind of score for experiment 1 looks like, and I'll just talk through it. So for the training set, I had 585 Java files, which isn't very much. And we also have in machine learning a validation set. And basically, machine learning models have this problem where they can overfit. And what overfit means is that they learn too much about the particular data set that you have given them, and they don't learn to generalize very well. Okay, so the real goal is that you want to train it on a data set, but you want to be able to make predictions on unseen data. So the validation set helps with that because it essentially is a cross validation set, and you can help pick up if your machine or if your model is overfitting or overgeneralizing. So the score it got was an accuracy rate of 52.1%. So what does this mean? Well, behind the scenes, what FastAI and ULMFit are doing is that they are taking that Java file and they are masking one of the words in that file. And basically, they're then asking the model to predict what you think that that word would be. So in 52.1% of cases, the model was able to accurately predict, which sounds good. But, okay, so what does that mean? Like, what does it mean? So I ran a little test. So I took this Java text public class base model, and I fed it into the model. And I asked it to predict what it thought the next 40 characters or 40 tokens should be. Do you want to do a drum roll and before I reveal what I came up with? Thank you. Next one is, this is what I came up with, which is pretty good. Like, to train something from scratch for this would take a long time. So you can see it's kind of got like, it's got the open curly brackets, it's got the semicolon in the right place. The array list isn't quite right. Array list is a Java class, but it's not camel case like it should be. So it's got a comment in there as well. And another one, public class base model, again with the same model, oh, drum roll, and I came up with this. So again, it's looking like Java code, like this is passable Java code. But again, you can see it's not quite getting the camel case. So I've done a small experiment. It looks like there's something valuable here, so I decided to try something else. So I'm going to add more data for the next experiment. And I did try run it on my laptop, and after about 6 hours, the fans were still whirring and buzzing, and it was my work laptop, so I thought, ooh, better stop. So I changed up the infrastructure a little bit. I used the Google Cloud instance, and this time I wrote my script that downloaded all the code from GitHub. I used Terraform to help spin up that cloud instance and made it really easy if I wanted to swap out the GPU. It's just a configuration change. And I also used DVC, which is Data Science Version Control. And this is like Git for large data sets. This was really useful, I found, when I was moving between my laptop and going to the cloud. It allowed me just to assume that the data would be in a local folder, and then I could use DVC behind the scenes to pull down whatever version of the data set I wanted to train on. So that was really useful. So experiment 2 was a bit bigger, so training set of 5,000, validation set of 1,000. We can see that the accuracy is going up, but what does that mean that the model can do? So again, public class, go on. And this is what I came up with, which is a bit, I'm really suspicious of real name. I think it sounds like what a machine pretending to be human would come up with as a class name. It's just, but you can see it's getting closer to that camel case, and we've also got a run method. So as regards generating Java code, I think this is pretty passable as Java code. So I put a tick next to that experiment and decided to move on to the next test. So can I generate Java code that will compile? And this was a little bit harder than what I thought it would be. So for this, I decided to move over into reinforcement learning, which is a little bit different to the supervised learning that I've spoken about before. Reinforcement learning is used where you see machines learning how to play games like chess. It's also used where robotics or robots are learning to navigate an environment. So it works a little bit like this. We have an agent, which is essentially your machine learning model, and it's operating in an environment. So it has actions that it can perform in that environment. So say this is chess, and the actions might be the pieces moving to a particular square. So you can move a pawn, a knight a particular way, a queen a particular way. And the environment passes back a state and a reward. So the state is like the state of the chessboard after it's been updated. And the reward is, you would give a reward when it does something well. So say, for instance, it had taken an opponent's piece, you would give a reward for that. Or it had checkmate, you would give a reward for that as well. So it sounds like there's a lot of stuff there if you wanted to build your own model. There's a lot of boilerplate code that you have to do. Luckily, there is a Python library framework for that. So OpenAI Gym, they have a lot of reinforcement models. Just added a box, you can use them. They've also got a lot of the boilerplate code. So if you're interested in reinforcement learning, in teaching machines how to play games, there's a lot of code there, and I recommend you take a look at it. So for this, I was looking for a way to create an environment that would enable the model that I had predicted that was able to generate code, to create an environment around that could that would give a reward and help the model learn when code was compiling that was a good thing, and just create that in that environment. So to do that using the OpenAI Gym framework, basically they have a class. You just implement these methods. The first one is step, so that relates back to the diagram that I showed earlier. So basically you take an action and then you send back the reward or the observation. Reset is just resetting the environment to initial state. And render is just more for the gameplay, gameplay reinforcement learning algorithms, so you can actually render the game to the screen. So again, most of the stuff is out of the box with OpenAI Gym. So I had to come up with some actions that would lead to a reward in this environment. So this is what I came up with. So the first one, action 1, generate Java code is the first part. Using our model, you give it a seed, public class, and then get it to generate what it thought the next Java token should be. And then check if that code compiles. So use subprocess, call that to Java C, and basically the error message or the message that I got back, I would parse. And if there was an exception there, I would note down the part of the code that the exception was in, the token that it related to. And the reward I would send back was if the code compiled, the reinforcement learning algorithm would get a reward. And the second action was just basically roll back to the first compiler. So we are going to have a vote. So if I ran this 10 times, who thinks that more than 8 times it resulted in a Java class or Java file that compiled? Ooh, 1, 2. Between 5 and 8, hands up. Cool. Between, say, 3 and 5. 2 or less? Okay, it's pretty split. Okay, the answer is 0. It was a lot harder to actually get something that compiled. I think some of the things are that my reward is just way too coarse. Waiting until something compiles to actually give it a reward. It might be better to see if there's some steps I can take, so break that down a little bit further. And yeah, so the next steps for this whole experiments that I'm running is go back and train the first model with more data. So 5,000 Java files is not very much to actually train with. I could easily train with 100,000 or 500,000, and maybe try and get close to having a model that can generate Java code that compiles from there. And then for the user reinforcement learning, just for the part of the test that I didn't actually get to, was to generate Java code that would pass the unit test. Use that more for the reinforcement learning part of the experiment. So takeaways. First one, don't assume things, experiment and test. So first one was that I didn't think that 500 Java files would actually get anything close to something that looked like it did, generating that Java code. And I wasn't actually going to even do that test, but I just said, start small, apply your principles. And it actually, it came up and it showed that it does work. The other thing was that I've kind of assumed that compiling code is a useful step in getting code that can pass a unit test, and that's why I went for Java. And it may well be, but I don't have a baseline to compare it to. So really when I was thinking about should have been Java or Python, I probably should have done a test for each and then evaluated which way to go forward based on that. Just enough, so just enough infrastructure, just enough data, always focusing on what the core piece of value that you are trying to deliver is. It's not building out amazing infrastructure. It's not running, using millions and millions of pieces of data. It's getting a machine learning model that can do something. So just enough infrastructure, and just enough data. And then start small. Start with something small. What is the smallest test? What is the cheapest test that I can do to prove that there is something useful here? So that is it. Thank you.